Computers are some of the most complicated devices that exist today, but all of their functionality can be broken down into a few basic operations. In this video, we'll learn how to program as close to computer hardware as humans can get. Although computers do maths using only zeros and ones, understanding these numbers can be quite confusing for humans. To bridge this gap, assembly language was created, providing a format that makes machine language easier to comprehend. There are many different assembly languages in use today, and which one you will use depends on the specific computer architecture of your device. In this video, we'll focus on the RISC-V architecture. Before you can dive into assembly, you need to know a few things about the insides of a processor. In the RISC-V architecture, there are 32 registers, each capable of holding 32-bit wide data. These registers together form what is known as a register file, which is usually built using SRAM or flip-flops. The registers are all used for different purposes, but for now, just think of each of these registers as simply a place to store data, which we might want to retrieve very quickly. If it doesn't really matter how quickly we access our data, we simply want to store a huge amount of information, we can use our memory. As we'll see later, the way our memory element is organized is a bit complicated, but for now, just think of it as a big block of data where we can store whatever we want. To perform useful tasks, we need to issue instructions, such as adding, subtracting, or loading data from memory. These instructions act on what are called operands, which can be registers, memory locations, or a constant. Now let's get to writing some assembly code. To test our assembly, we're going to use a simulator called Venus. If you want to use it yourself, it will be the top link in the description. For this video, we're only interested in the editor and the simulator tabs. The editor tab is where you write our assembly, and the simulator tab is where we run our assembly. On the right here, we can even see our registers and our memory. To indicate the start of our file, we write _start followed by a colon. Any line below this will be ran from top to bottom by a machine. Although not necessary, we'll put an indentation here to make the code easier to read. The simplest instruction we can start with is called the add instruction. It simply takes in two registers and adds them together. The result gets stored inside another register. Let's use the registers S0 through S11 for our computations, or registers 8, 9 and 18 through 27. Let's add S0 and S1 and store the result inside S2. Another way to write this would be like this. Now we've made our first line of code, but this really isn't all that useful since our registers usually start out as a 0, meaning that we just did 0 plus 0 equals 0. To do more useful things, we want to initially load a constant into registers. These constants are called immediate, and they're always 12-bit, 2's complement numbers. The instruction to add an immediate is add I. Here you can see what it looks like to add 2 to S0. We don't just have to write these numbers in decimal. By putting 0x or 0b in front of them, we can write them in hexadecimal and binary respectively. Let's now try to calculate the sum 5 plus 3 plus 6. Our first step is to add 5 plus 3, and then we should temporarily store the value in a register. As a convention, people decide to use the registers T0 through T6 to store temporary values like these. Or in other words, registers 5, 6, 7, 28, 29, 30 and 31. So we could set S0 to 5, S1 to 3 and store the sum in T0. Then set S2 to 6 and store the final result in S3. The type of instructions which take in two registers and write the output to a third register are called R-type instructions, or register type instructions. We've already seen the add instruction, but you also have subtract and a few others. Here you can see all of them in a table. Let's try to do this sum, 6 minus 3 plus 21. As before, set S0 and S1 to 6 and 3 respectively, and then store the difference in T0. We can set S2 to 21, and then store the sum of S2 and T0 in S3. If registers were the only components we could control, then our assembly programming wouldn't be as interesting. So let's take a look at our memory. Whereas our register file is small and fast, our memory is larger and slower. For this reason, variables we use very often are kept in registers. RISC-V instructions can only act on registers, so the only thing we can do with our memory is to store data to it or load data from it. Our memory is arranged to have a width of 32 bits, but since a bit is a small piece of information, people decided to break up every group of 8 bits into something called a byte. So a data word consists of 4 bytes. Our word address is then always a multiple of 4. So we start at 0, then the next word is at address 4, then the next one at address 8, and so on. Let's now actually use our memory. The store word instruction and the load word instruction are exactly what we need. Store word, or SW, for storing data in memory, and load word, or LW, for loading data from a memory to a register. The syntax of them is a bit unusual though. The first thing you write down is simply a register, but then you write an offset added to a register behind it in brackets. For example, let's say set S0 to 4 and S1 to 2. If we want to store our 4 at address 20, and then again read our memory and store it in register S2, we would want to write this. This 18 here is so that the 18 plus the value stored at S1 add up to our wanted address. It would be simpler if we just used a register with a value set to 0. Then you could just write the actual address we want to store or load something at here, and not have to worry about an offset. But lucky for us, that does exist. The first register, in fact, is called a 0 register. The amazing property is that its value is always 0. Even if you try to change it, it won't work. This also gives a better way to initialize the value with ASCII. Hoping that the initial value is 0 is not as safe, because if, for whatever reason, the value isn't 0 at the start of your program, it might not run as expected. To create better code, you not only have to think about safe code, but also about stylistic choices of your code. You've already noticed that an indentation doesn't change the actual behavior of your code, but neither does a whitespace. This allows us to break up different parts of our code into segments, each with a specific function. Another way to improve our code is by using comments. You create a comment with a hashtag symbol, and everything to the right of this comment will be ignored when it comes to actually running your assembly. This means you're able to create mental notes to yourself when coding. Conventionally, comments are either placed above a block of code to indicate what it does, or to the right of a line to explain how that specific line works. Writing code wouldn't be as interesting if your code always did the exact same thing, so people have invented branching, which allows a processor to take different paths through a program. You might have already heard their names in other programming languages, such as if-else statements, switch statements, for loops, while loops, and so on. But before we can talk about that, you have to know something about the program counter. Our memory element isn't just used for storing data we want to use, but it also stores our actual instructions themselves. If you go back to our previous example, you can see that when you store the value 4 at address 20, we indeed had 4 in our memory, but the address 0, 4, 8, and 12 also contain the actual lines of assembly we wrote. Meaning that the instruction to store the value 4 in S0 is 0x00400413. Inside of the processor exists a counter called the program counter, or PC for short. This counter starts at 0 and keeps incrementing by 4. The value of the PC indicates the current address that is being accessed from memory and that's being run. For example, at the start of a program, the PC starts at 0 and runs the code stored at memory address 0, then becomes 4 and runs the code stored at memory address 4, then becomes 8, and so on. The way we can implement our branching is by changing the value of our PC. For example, if we want to keep repeating the same line of code over and over again in what is called a loop, we could run a line of code and then subtract a value from our PC. Likewise, if we want something called an if statement, we could check whether two registers are the same, and if they aren't, we continue our code, but if they are, we increase our PC and skip over that code. The if statement I just talked about actually has a name. It's called branch if equal, or just BEQ for short. You also have branch if not equal, which is BNE. You have branch if less than, BLT, which branches if the first register is less than the second. And you have branch if greater than or equal, BGE, which branches if the first register is greater than or equal to the second register. BLT and BGE treat numbers as signed, but you also have BLTU and BGEU, which treat them as unsigned. Let's now actually use one. Let's say we have some initial register S0 and want to check if it's divisible by 2. If it is, you want to divide by 2, and if it isn't, you want to keep it the same. Let's start by initializing our S0. We know that something is divisible by 2 in binary if the last bit is a 0, so you just need to check the last bit. We can't do that directly since you always need to compare two registers, but a trick we can use is to put a number in an AND gate together with the number 1. This is the effect of turning the last bit to a 1 if it's odd and to a 0 if it's even. Let's use a temporary register T0 to store our 1. Let's use T1 to store T0 and S0. Now if T0 and T1 are equal, we want to jump to the end of our code and not do anything. But if they aren't, we can continue our code as usual, meaning that we need a BEQ now. The syntax for BEQ is the two registers you want to compare, together with a label you want to jump to. Let's call our label done, since we're done with our code at that point. You write these labels without any indentation, with a colon after them. For our code here, we just need to divide by 2, which in binary is similar to dividing by 10 in decimal, meaning that all we have to do here is just remove the last 0. This can be done with this shift right arithmetic command, SRA. We only need to shift one place, so we can use the T0 we had, since that's 1 anyway. Let's try our code for a few numbers. As you can see, our code functions correctly. Let's now look at loops, for which we first need the jump instruction, or simply J for short. The jump command simply jumps to the label we write after it. For example, in the code we previously wrote, if you add a label here called check, and after divide by 2, we jump back to check, then we have created code which continuously divides by 2 until our number is odd. You can even use another register like S1 to keep track of how many times we divide by 2, like this. As you can see, in the number 64, we can fit exactly 6 2's. What we've created here is commonly called a while loop. It keeps repeating itself as long as this condition here is false. You can also keep repeating as long as it's true, or maybe greater than or equal to some other register. You can also create what is called a for loop, which you can use if you want your code to repeat a certain number of times. Let's say you want to add a number to itself 10 times. So 1 plus 1 equals 2, 2 plus 2 equals 4, 4 plus 4 equals 8, and so on. Let's store the initial number 1 in S0. For your for loop, you'd usually create two variables. One for how many times you've repeated the loop so far, and one for how many times you want to repeat the loop in total. Let's set T0 to 0, since we didn't go through the loop at the start of the program, and set T1 to 10, since we want to repeat this 10 times. Now we just finished the corresponding loop mechanic, where your branch of T0 and T1 are equal. Don't forget to add 1 to T0 every time we go through the loop. Then just add S0 to itself, and we are done with our code. And as you can see, our code works. You can even try different starting conditions, or repeat the addition more often. With these basic R-type instructions, if statements and loops, you can already do a lot. This is because in programming, you'll keep combining these basic tools together to create the complicated behavior you want. One way to keep getting more complicated behavior is with something called abstraction. This is a process of hiding details which are not important. When we want to use this code, we don't actually need to know about how it works and why all of the instructions are where they are, but instead, we just need to know that this component keeps adding itself over and over again 10 times. Using abstraction, we can keep thinking about more and more complicated problems. Because if every engineer had to keep thinking about every single transistor to make a computer, we wouldn't have come very far. And one way to implement this using code is with functions. Functions are machines which have some inputs, called arguments, and one or two outputs, called return values. When a function is working, it might also have some side effects, which we'll see later. To use a function in your code, you need to call it. When one function calls another function, then the original is called a caller, and the function that's being called is called a callee. A function is a block of code further in your memory, and you might think we can just use the J instruction to jump to the function and use it. And you wouldn't necessarily be wrong, but one property of a function is that when you're done running the function, you should go back to where you left off your code. This means that we have to store the PC address we're currently at in a register before we jump to our function. The register where this address is stored is commonly called the return address, or register number 1. The instruction to both store the address we should continue from and jump to the function of interest is called jump and link, or JAL for short. The syntax is JAL and then the register you want to store the return address in, which conventionally is RA. And then finally, the label of the function you want to jump to. Writing RA here is so common in fact that we don't actually need to include it. So we can just write JAL and then the function, and we still have the exact same behavior. Now that we've called our function, we can run some code, but once we're done, we need to go back to the address given in our return address. This can be done with a jump register instruction, or JR for short. The syntax is simply JR and then the register you want to jump to, which is RA. Alright, let's try it out with an example function. Let's say we have a function called add2, and all it does is it adds 2 to register as 0. For the function, we simply implement the behavior we want, and then jump to the return address with our final JR/RA. It's as simple as that. Let's now write the code to call the function, which is just as simple as JAL add2. But before we run, let's initialize the value of S0 to 0. We can even implement a loop from before. Let's say we want to add the number 2 10 times. We initialize the first two variables, starting at 0 and ending at 10. We create our loop and run our function, and then we check whether t0 and t1 are equal. If they aren't, we go back to our loop. As expected, when we run, we get our value of 20 for S0. Our code is indeed correct, but you could argue that there are flaws in its design, specifically how dynamic it is. What if we want to add 5 instead of 2? What we've created is a function with no inputs and no outputs, but just as a side effect of adding 2 to S0. When we want to have a function use different inputs, we can use registers A0 through A7, or registers number 10 through 17. For outputs, we use registers A0 and A1. Let's go back to our code and use two inputs. The first one can be the number to which we're adding, which was the value of S0 in this case. The second input can be the number we want to add, which was 2 in this case. So let's add A0 to S0 and A1 to 2, and we get this for our input. For our add2 function, we no longer want to add anything to S0, but instead we want to add whatever is stored in A0 to A1. The result of this calculation will be our output, which as we said before, is conventionally A0. Then we return to the original line of code, and we still want to store the result in S0, so we can do that here. As you can see, it still does the same thing as before, but now, let's say we don't want to keep adding 2, but 5 instead. We can change that here. As expected, we get a value of 50 in S0. In case we want to use more than 8 registers of inputs, we can use our memory. But as we've seen before, the memory is more than just a place to store variables and instructions. With memory addresses that are 32 bits wide, we can access 2 raised to the power of 32 addresses, or 4 gigabytes of addresses. Since the instructions are aligned to multiples of 4, they can range from 0 to 0x FFFF, FFFC. We can break up our memory into segments, each storing data for specific purposes. The specific way we divide our memory is called a memory map. Since the RISC-V architecture doesn't provide a specific memory map that people should use, we'll just show you an example map here. On the bottom of our memory, we have exception handlers and some firmware, which is software permanently stored on a device. This firmware can contain programs automatically run on startup and programs for the operating system. A bit higher in our memory, we have our text segment. This is the place where our machine code is stored. This is our computer program, but now turned into actual zeros and ones. These are the actual addresses that our PC goes over to execute our code. After this, we have our global and dynamic data, which contain our variables. To understand the difference between these two segments, you need to understand the differences between global variables and local variables. There might exist some variables that get created at the start of the program that can be accessed everywhere in your code, the so-called global variables, which get stored in our global data segment. Then you have local variables, which get created while the program is running, and whether they can be controlled by other functions or not depends on the specific code. These get stored in the dynamic data segment. One advantage of differentiating between global and dynamic data is that the size of global data can be decided at the start of the program. We don't have to worry about accidentally wasting some memory. Another way to make this more efficient is by using a global pointer register, or GP for short. It's register 3 in our register file, and it contains the address right in the middle of our global data. The advantage of this is that variables close to the center of our global data can be accessed very quickly, as we'll see later. The dynamic memory is more complicated as well. It consists of two parts, the stack and the heap. The stack is the stop region of our dynamic memory. It operates in something called a last in, first out manner, or LIFO for short. Similar to putting a bunch of plates on a stack, the last plate you put there will be the first one you can remove. Likewise, if you put a piece of data in our stack, the last piece of data we put there will be the first one we can remove. This can be very useful for function calls and local variables, because the structure of a stack makes it very simple to remove this memory from the stack, or deallocate the memory, so to speak. The stack typically grows downwards, where it gets bigger if we add more data. The way we control the stack is with a stack pointer, or SP, which is register number 2. The stack pointer points towards the top of our stack, and by decreasing its value, we can reserve or allocate possible memory in the stack we want to use. And by increasing it, we can forget or deallocate data we have previously stored in there. The heap, on the other hand, does not follow a simple LIFO structure. Instead, we can allocate and deallocate memory on there in any order we wish. This of course gives us more control as the creator, but this also means that the process of allocating and deallocating memory is more complicated. We typically let the heap grow upwards in our dynamic memory, but as you can imagine, this might cause a problem. What happens when a stack, which grows downwards, and the heap, which grows upwards, hit each other? We get something called stack overflow and heap overflow. Stack overflow when you perhaps call a function too many times, and heap overflow might happen when we forget to deallocate memory. Finally, the top part of our memory might be used for the operating system and memory mapped I/O, which is beyond the scope of this video. That was a lot of information, so let's try out some of these new structures, starting with the stack. Let's first simply try to store registers S0, S1 and S2 on the stack. Let's set them to 4, 5 and 6 respectively. First, we want to allocate enough memory on the stack. We have 3 registers, which are all 4 bytes wide, so that brings us to a total of 12 bytes of memory we want to store. So we need to decrease the stack pointer by 12. Although this will work, we usually want to allocate a stack pointer in multiples of 16 to be compatible with other machines that only work in multiples of 16. Now just use the store word instruction to store off the corresponding registers. Keep in mind that we need to add 16, 12 and 8 to align the data. As you can see, this code functions correctly. But this was a simple example. Let's try to do something harder now. Let's say we call a function A, which itself calls a function B. We call functions using JAL, and we return using JRRA, so you can write that down. Right now, it's hard to figure out what is happening exactly. So let's say at the end of our start, we set the value of A0 to 0, at the end of A, we set the value of A0 to 1, and at the end of B, we set the value of A0 to 2. If we try to run our code now, it will never finish running. To figure out why that is, we can run through our code step by step. At first we call A, setting RA to the address running this line of code. A calls B, setting RA to the address running this line of code. Then we set A0 to 2 and jump back to our return address, which sets A0 to 1. Now we jump back to our return address again and set A0 to 1 again, and then once again jump back to that line of code in an infinite loop. The problem here is that we need two separate return addresses, one for returning to this line of code and one for returning to this line of code. This is why the stack is used for function calls. We can always just store the return addresses in the stack. Let's start A by allocating 16 bytes of memory on the stack, and then store the current return address. Don't forget to also deallocate this memory at the end and load the previous return address. As you can see, the code functions correctly now, running A, then B, and then finishing by setting A0 to 2. The main lesson to be learned here is that for a non-leaf function, which is a function which calls another function, you need to start it by allocating memory on the stack and storing the return address, and then finish by loading the return address and deallocating the memory again to prevent the stack overflow. A similar thing can be done with local variables inside a function, which we'll look at now. Let's create something called a recursive function, which is a function which calls itself. For example, we can make a function which calculates the sum of all integers below its input. So if you input 1, you just get 1. If you input 2, you get 1 plus 2 equals 3. If you input 3, you get 1 plus 2 plus 3 equals 6, and so on. Because this function is a bit more complicated to implement than the ones we've seen before, let's first write it in something called pseudocode. This is simply writing the algorithm using comments first, before replacing them with actual code. The way we implement this using recursion is that this function for an input of, let's say, 5 is the same thing as 5 plus sum of integers of 4, which again equals 5 plus 4 plus sum of integers of 3, and so on. To prevent this from running forever and getting a stack overflow, you always need a base case in a recursive function. In this case, that's just checking where the input of sum of integers is 0. If it is, we return a 0. The first thing we realize is that this is a non-leaf function, because it calls another function. So we need to start and end with allocating and deallocating memory, as well as storing and loading RA. What should we write for our main code? First, we should check our base case, that is, checking where the input is 0. Then we need to call our function for the input -1 and add that to our current input. There's one part that's still wrong though. When we pass the input to our function, such as in this line, we need to store our input in register A0, but when we decrement our input, we also forget what our original input was for this line. The way to fix this, of course, to store our input on a stack. Now, let's go about actually writing our code. Since we need to store 2 registers, we need to allocate 16 bytes of memory on the stack. We can store our registers by using the load word instruction. For our base case check, we can add a label here called base case to skip the function call. Then we just call our function for the input A0 -1, load our input to T0 and add that to the output of our function call A0. Now just finish the rest of this function as usual and we're done with our code. As you can see, it works correctly if we try, for example, an input of 50. Before we take a look at the global data segment, let's first learn about what are called assembler directives. The assembler is what turns our assembly code into actual zeros and ones, and assembler directives are instructions that aren't turned into zeros and ones, but for our assembler to organize our code. The assembler directives that are supported depend on a specific assembler, but on the Venus simulator, we can use these assembler directives. The data and the text directives tell whether code should be stored in the global data segment of the memory or in the text segment, respectively. To use such a directive, you write a dot and then the name of your directive. For example, if we want to store the instruction to set S0 to 2 and S1 to 5, we would have to write this code. The code wouldn't have actually changed if we removed the directive in this case, but in this way we made it clear to the assembler where exactly the instruction should be stored. To use the data directive, you also need to use one of these 5 directives: byte, ASCII-Z, word, float, and double. Byte and word are pieces of data with a width of 1 and 4 bytes respectively. Float and double are to store floating point numbers, which you can see an explanation of in our previous video. But in short, they're just a smart way to store real numbers. They are 4 and 8 bytes respectively. Finally, the ASCII Z directive is to store a null-terminated string, which I'll explain in a bit. Let's say you want to store 1 byte of information, maybe the number 5, in our global data segment. We start off with .data to indicate to the assembler that any variables below this should be stored in a global data segment. Then we write the name of our variable, which with the exception for built-in names and dots and dashes, can be basically anything. Let's call it my_variable. Then we'd follow this by a colon and write .byte, followed by the value you want to store, in this case 5. Sure enough, if we take a look at our memory segment, we indeed find the value 5. If we want to store a value above 255, we would have to use the word, float or double directives. We can also use the variables we have defined in our data directive. Let's say we have two variables, x and y, which point to 5 and 6 respectively, and we want to add them together and store the result in S0. If we naively try to write this code, it won't work. This is because these variables, x and y, don't actually contain the values 5 and 6, but rather the addresses in the global data segment. So x is not 5, but 0x10000000, and y is not 6, but 0x10000004. To add these numbers then, we first have to load them into some registers, T0 and T1, which can be performed by the load word instruction. But if we try this, it still doesn't work. This is because our addresses are too high. The immediate offset can only be 12 bits wide. Luckily, with the load address instruction, with which we can load x into T0 and y into T1. Now we can use load word and proceed as before. As expected, we find a value of 11 in S0. As for the other two assembler directives, a global directive is used to make a symbol global, which means it can be used by other files. This is especially important if your file contains one main function where all of the action happens. For example, in our previous code, we would make the _start function global to indicate that this is the entry point of our program, and that is global without an A. If we want the variable x to be visible to other files, we can make it global as well. Finally, for the align directive, what it does is it aligns the next piece of data or instruction to a boundary for power of 2. For example, if we store global variables x and y, each with a width of 1 byte, we can see that x is 0x10000000 and y is 0x10000001. However, if we write .align 1 just before y, then y can no longer end in a 1, because 2 raised to the power of 1 equals 2. It must change its value so that the last digit here is a multiple of 2. Likewise, if we write .align 2, then 2 raised to the power of 2 equals 4, and y must be divisible by 4. .align 3 would mean divisible by 8, and so on. So if you make global variables using the .data directive, then what is the point of the global pointer register? It basically allows us to save one line of code when retrieving a variable. For example, if we define variables x, y, and z like this, we can put the values of x, y, and z in registers S0, S1, and S2 using the load word instruction relative to GP. In this case, the register GP contains the value 0x10000000, which is the start of our global data segment. By adding 0, 4, and 8 to this, we get x, y, and z. Sure enough, if we run this code, we indeed find 5, 7, and 15 in S0, S1, and S2. In case our global data segment became larger, we could move the GP register to point towards the middle of the segment. This would give us the largest reach to variables stored there. Before we start talking about the heap, let's take a look at something called environment calls, or ecalls. Ecalls are instructions which request a service from the operating system, and here you can see all of the possible ecalls in the Venus simulator. For example, the first one tells us that if we put 1 in A0 and perform an ecall, the value of A1 will be printed. Let's try it out by setting A1 to 5 If we go over our console, we can see that we indeed printed the number 5. We can also see that setting A0 to 10 and then requesting an equal ends the program. If you try setting S0 to 5 after our equal, we can see that the value of S0 is never set to 5. Meaning that the proper way to end the underscore start function in this simulator is by setting A0 to 10 and equaling. The reason I brought these equals up though is to teach you about Sbrk and Malloc and free. They are system calls used to allocate or deallocate memory from the heap. In Venus, the heap starts at address 0x10008000 and grows upwards. Sbrk is used to request a specific amount of bytes from the heap. For example, if we want to store a 4-byte word, such as the number 100, we would proceed as follows. Put the number you want to store in a register, such as S0. The ecall ID for A0 is 9 in the case of Sbrk, so set A0 to 9. And set A1 to 4, since we want to store 4 bytes of data. We haven't yet stored S0 in memory now, but if we take a look at A0 in a register file, we can see that the value is now the starting address of our heap. This is because Sbrk returns a pointer to where it can store our variable. Pointer just being a fancy word for address. So all we need to do is just store S0 and A0, and as you can see, it functions correctly. To store more data, we just repeat our Sbrk call. For example, if we want to store the number 0 through 100 in our heap, we can just implement a loop. If you use Sbrk every time we go through a loop to request 4 bytes in a heap, we can store the current loop index, T0, in the heap for every number. As you can see, it works just fine. So, if you can use Sbrk, then what are Malloc and free for? Malloc stands for memory allocate, and it's an abstract function used to allocate memory on the heap. Free is an abstract function to deallocate this memory. In the Venus simulator, Malloc and free can be used by setting A0 to 0x3cc and then setting A6 to 1 and 4 respectively. Malloc takes the amount of bytes you want to store in A1 and returns a pointer to that block in A0. Free will free the pointer given in A1, which means you just deallocate some memory in the location it pointed to. Let's try to store the number 5 in the heap, but this time using Malloc and free. Let's start by setting S0 to 5 to be stored later. Then we need to call Malloc to request 1 byte of data and store S0 in that byte. Now we're not done, because whenever you call Malloc, you also have to call free in case you don't want a heap overflow. So let's now free this block of data. And now that we've called free, we can say that we're done. Also notice how if you swap lines 14 and 15, this code wouldn't have worked. I want to be clear that Malloc and free aren't really RISC-V instructions, but they are higher level functions part of something called the C library. As promised, we still have to talk about the ASCII Z assembler directive from before. It's used to store words or sentences in it. To store a sentence, you first need to store individual characters. We could make up some rules to convert numbers to characters, such as 0 equals A, 1 equals B, 2 equals C, and so on. But some American people create the American Standard Code for Information Interchange, or ASCII for short, which is the most common encoding used today. Here you can see all of the ASCII characters relevant to writing sentences. For example, 0x41 would mean capital A, 0x75 would mean lowercase u, and so on. If we want to print out a character in the console, we could do so using an environment call. By setting A0 to 11, we can print the character in A1 to the console, so let's try it out. Let's try to print uppercase M to the console. If we look at our ASCII table, we can see that uppercase M is 0x4d. Let's store that value in S0. Now just set A0 to 11 and equal to indeed find uppercase M printed out in the console. Let's now try to print out a whole word, such as hello. Let's start by storing all of the individual characters in our global data segment. Let's create a loop that goes over every letter. Since every character is stored at the start of a global data segment, each spaced 4 bytes apart, all we have to do is load the word into A1 and decrease GP by 4. Now actually print the character and finish the program. And as you can see, it does indeed work. What we've just created is called a string, which is an array of characters. Strings don't have a fixed size, as you can always just add more characters to it, and it will keep growing. This variable size does make it much harder to work with them though, so what people have decided to do is put a null character as the last byte. In ASCII, the null character is literally just the number 0, and it indicates that the string has ended now. This is where we use the ASCII-Z directive. By writing ASCII-Z and putting text in quotation marks, we have created a string stored in a global data segment that ends in the null character. Let's now try to print the string hello world to the console. We can use environment call to print a string. We have to put the address of the string in A1 and set A0 to 4. To find the address of our string, we can just use the load address instruction. Let's end our code, and as you can see, it's working. Now that you already know a whole lot about RISC-V instructions, I do have to reveal that some instructions that are introduced aren't real instructions. These being J, LA, and JR. They are what we call pseudo-instructions. Pseudo-instructions are combinations of one or more different instructions. For example, the J instruction actually means jump and link, 0, and then the actual label you want to jump to. Some of these can be very useful for simplifying code. For example, the load immediate instruction, LI, is a pseudo instruction, which, just like ADI, can be used to set the value of a register. However, with ADI, our immediate can only be 12 bits wide, which means that we've combined ADI with a load upper immediate instruction, LUI. The load immediate instruction simplifies all of this, allowing us to simply write down the immediate we want. Here you can see a list of the most common RISC-V pseudo instructions. And here you can see a list of all real RISC-V instructions. If you look closely at the bottom here, you can see that there are some instructions which don't take an input register, but instead take in a CSR. CSR stands for Control and Status Register. They are special registers used for a variety of things, such as interacting with hardware features, managing and measuring the internal state of the processor, and more. They also introduced a new idea of something called privilege levels, which can be used to change what piece of memory you can control and what instructions you can run depending on the level you're in. Here you can see the 4 privilege levels in RISC-V. Since this video is long enough already, I won't go in depth about how CSRs and privilege levels work. Let's do a quick recap of everything we've done so far. The RISC-V instruction set architecture consists of these instructions, which can be combined to create assembly code. When creating assembly code, we make our code more useful with structures such as if-else statements, loops, and functions. By combining these structures, we can make our code more abstract and solve more complicated problems. These instructions act on registers, which are small devices which can store zeros and ones. We have 32 of these registers, each of which can hold 32 bits of information. Together, they are known as the register file. The instructions also act on our memory. This is a place consisting of, among others, the text segment, the dynamic data segment, and the global data segment. Our assembly code is turned into zeros and ones by a program called the assembler, and then stored in the text segment. By increasing its value in steps of 4, the PC can run each line of code in the text segment. The global data segment and the dynamic data segment are used to store global and local variables respectively. To make it clear to the assembler exactly where all of the assembly code you wrote should go to, you would use assembler directives. .data and .text indicate whether to go to the global data segment or to the text segment. And then you also have CSRs, which are special registers used to do more complicated actions related to the OS and exception handling. But what would it look like to use RISC-V in real life? In case you want to use more sophisticated simulators for RISC-V, to learn more about the ASCII, you can use simulators such as Spike or Sail RISC-V. You also have emulators, which go a step further than simulators. Instead of mimicking the behavior of the logic systems at a high level, Emulators replicate internal hardware, such as registers, memory, and CPU behavior. This means emulators can run real RISC-V code. Some common emulators are QEMU and TinyEmu. Then you might also want a cross-compiler toolchain, which consists of a compiler, an assembler, a linker, and a debugger. Believe it or not, but although we've been writing code in assembly this whole time, in real life that isn't that common. Instead, it's more common to write in higher level programming languages, such as C or C++, which remove a lot of the complexity assembly brings us. But of course, we still need to run assembly. It can't directly run C code. That's where a compiler comes in. A compiler is a computer program which turns this high-level code into assembly. The reason why it's a cross-compiler rather than just a compiler is because the device you might write these programs on probably isn't running RISC-V, but instead assembly languages such as x86 or ARM. The cross-compiler still runs on the x86 or ARM device, but creates RISC-V assembly code. You already know the assembler, which is simply the program that turns RISC-V code into zeros and ones. The linker is a related program, which combines different machine code files into one bigger file. The debugger is something we haven't touched in this video, but it's basically a program to diagnose issues in your code. When it comes to installing a toolchain, you can either download a pre-built toolchain or build your own. For pre-built toolchains, you can download the RISC-V GNU compiler toolchain or the Sci-Fi Freedom toolchain, which is an American company which makes RISC-V processors. Or of course, one of the many other toolchains online. In case you want to customize your toolchain or get the latest features, you can also build your own toolchain. How exactly you do that depends on your specific OS and the goal of your project. These projects are usually hosted on a website called GitHub. GitHub is a pretty big service, incorporating the software Git. A very high-level explanation is that GitHub is a website that uses Git to keep track of different versions of a project you're working on. All of the files of a project are stored in a repository or a repo. If you want to download the files of someone's repository, you can either use the Git software if you have it installed, or click Code and download zip. Then you need to extract it to use the files. In case you don't really know what everything is, you can scroll down to read the README file. This usually contains explanations of what the project does and how to use it. In case you still run into problems, you can click the Issues section to see problems other people had, or make your own issue to report a problem. That's all we'll say about GitHub and Git in this video, but you'll see them come up over and over again if you program many things, so it's worth taking the time to get to know them. Now we still need a place to write your actual code. You can use very basic places like the Notepad to write your code, but there exists a better place to write code, called the text editor. It can add nice colors to your code, as well as give you a wide variety of shortcuts and plugins to speed up your work. Here are some popular text editors. Most likely though, you will use an integrated development environment, or IDE for short, which tries to put as many useful features for writing code into a single program, such as a text editor, a compiler, and more. So now that you can write, compile, and test the code using the tools previously mentioned, you can put it on a physical board. The simplest and cheapest physical board would be a microcontroller. This will contain a RISC-V CPU, which will be running your code, as well as some peripherals to get inputs and outputs, so your code can make smart choices based on the environment, rather than just calculate and store numbers like we've been doing so far. If you want to use a bit more expensive board, you could use the development board, which has a few more useful components to make it easier to prototype with. For both the development board and the microcontroller, you would also need to flash the zeros and ones from the computer you're writing your program on to the device. Once again, software to flash the firmware comes in a wide variety, but here are a few common ones. And finally, more complicated hardware would be the FPGA. Here you have to make your own RISC-V CPU or use a pre-built one, which wouldn't be written in a normal programming language, but instead in something called a hardware development language, or HDL, such as VHDL or System Verilog. Please let us know in the comments if you'd like a whole video dedicated to them. Your HDL file will then be converted into a bit stream, which can then burn onto your FPGA. This video was of course just a tiny part of the RISC-V instruction set. In this video we used instructions for the RV32i, which uses 32-bit registers, which also have versions which use 64 or 128-bit registers. You can add extensions to the base ISA. For example, with the M extension, you get access to new instructions like multiply and divide. You can even create your own extensions with custom instructions. If you'd like to learn more about all of this, you can read the RISC-V Documentation, which will be the top link in the description. But before you do that, click on this next video to figure out how to make your own RISC-V CPU.